All right, welcome everyone. Today we're going to be talking about polar lengths. So we're going to see specifically how to calculate the length of a polar curve. And it comes down to one formula. So let's look at this formula. All right, so the length of a polar curve, and it's going to be written in the form r equals a function of theta. And this will be over some, possibly specified interval. So we're looking at the length of a polar curve in the form r equal to a function of theta, where we're going to be looking at this length over an interval of theta. So theta might be between a and b. All right, so what is the formula? Well, the length is equal to the integral from a to b of the square root of r squared plus the derivative of r with respect to theta squared. Now there is kind of one, little condition here that we don't really have to worry about too much, in the problems and examples we'll be looking at. But we do require that the derivative f prime for our polar curve is a continuous function on this interval. So dr d theta or f prime, however we're calling this thing, needs to be a continuous function f prime. All right. So there is two kind of scenarios here that we'll be looking at. One is where the interval for theta is actually kind of given to us. It's kind of specified. But sometimes if this interval for theta is not specified, then we actually have to figure this out. So the interval for theta here, and if it's not specified, what we really want to do is we want to find the theta values that trace out the curve exactly one time. So we know polar coordinates tend to repeat themselves. So polar curves, once you get far enough around, generally, not always, but usually, a lot of times, they start repeating over themselves. So you start tracing over the same curve multiple times. So if this interval for theta is not specified, well, then we need to find the theta values that trace out the curve exactly one time. And generally, how do we do this? Try to sketch the graph. Normally, that's a good way to do this, is just try to sketch the graph of the polar curve. And eventually, once you get around far enough, you'll find the theta value where you end up back where you started and you start tracing over the same curve again. All right, so let's look at an example. Example 1. We're going to set up the integral that gives the length of the polar curve r equal to theta, and here the interval is specified for us. So the theta values are going to be from 0 to 2 pi. And we looked at this curve when we first talked about, last time, when we talked about the area enclosed by a polar curve. So what did this thing look like? Well, it spiraled away from the origin. So it started at the origin when theta was 0. And then as we move around counterclockwise, it spiraled away. So what did we get? We got a few points here. So we got this as we spiral away around counterclockwise. Let's do it in segments here. Kind of get this like snail shell almost. It's spiraling away from the origin here. And what we're going to do, this is from 0 to 2 pi. So at theta equals 0, this polar curve starts with a radius of 0. And then at pi over 2, the r value is around 1.5, 1.6, somewhere in there. So we're about that many units away from the origin here. Then at pi, if we plug theta equals pi into this, tells us the r value is pi as well. So we're about 3.14 units away from the origin here. And then at 3 pi over 2, I think it was like 4.5 roughly. And then at 2 pi, we're about 6.28 units away from the origin. So we're just spiraling around here as we move counterclockwise. And so what we're going to do is we're going to set up the integral that gives us this length. So the length is going to be the integral from 0 to 2 pi. It'll be the square root. And let's just write in what the formula is. It's r squared plus the derivative of r squared. And we're going to be integrating with respect to theta. So let's fill in for this r squared. Let's fill in what r is equal to in terms of theta. So we'll get a theta squared there once we fill in. And then let's calculate what the derivative of this function r is with respect to theta. So what is the derivative of this function? Well, we're differentiating with respect to theta, so theta is our variable. Derivative of this is just 1. So dr d theta is equal to 1. So when we plug in the r squared here, because our polar curve, we get theta squared. And then when we plug in for dr d theta, we're going to get plus 1 squared. And so if we simplify this, we have the integral from 0 to 2 pi of the square root of theta squared plus 1 d theta. All right. So the directions just ask for us to set this up. So this is good. We can stop here. Now, if we actually did want to go through with this, and it's a homework problem, how would we do it? Well, square root function, 1 plus a variable squared, trig substitution. Now, theta here it's our variable here. So when we do a trig substitution, this isn't necessary for the setup here, but if we did want to integrate this, if we wanted to go further with this, what would we do? Well, we see 1 plus our variable squared. So for a trig substitution, there's 3 options. And this option is for the when we have the plus there, that's for the tangent substitution. So we would do theta is equal to tangent of, let's use some other, maybe w or omega if we want. So maybe we do a trig substitution where we let theta equal to tangent of, let's just call it w. And then go through the regular trig substitution steps. So this is going to be our substitution. Let's calculate the differential. So what is the derivative of tangent? Secant squared d theta, or dw, rather. And then what would be the square root term? Well, how would that simplify? And it's bugging me. I like to write my square root terms like this as 1 plus. So I'll just write it as 1 plus theta squared. And how I remember this trig substitution is when I see the plus, kind of think of it like the tan here. So I write my t's kind of like pluses. So when I see the square root term, constant plus a variable squared, I'm thinking the tan substitution. So what does this square root term become? Well, it just simplifies into secant w. So it kind of goes through this, it's the opposite trig function. So our trig substitution was tan. The square root term here simplifies into the opposite one. So secant w here. And by opposite, I mean, there's that trig identity of secant squared is equal to 1 plus tangent squared. So you can kind of run through the steps there. All right, so yeah, how we would actually go through this, how we would actually do this integration is with a trig substitution. We would want to go through our usual trig steps, and this is what we would do. We would have theta, we would calculate d theta, and then see how that square root term simplified. Oh yeah, one other thing. I knew I wanted to mention something else. Normally there's a constant here in front of our trig value, but that's related to this extra constant that we have here. So really normally the trig substitution is a times tangent, and the a value is just the square root of the number here. So the number that goes in front is the square root of that, and square root of 1 is 1. All right, so this is how you would go about finishing this problem off. But we got the integral set up. All right, let's try another one. So this integral would give us the length of this polar curve, but we were given the actual theta values, the interval to actually consider. Let's look at example 2. So here we're going to find the length of the polar curve given by r equal to 3 cosine theta. And here we're not actually given the theta values. So we have to figure those out. And what we need to do is we need to find the theta values that trace out the curve exactly one time. So if we use the theta values where we actually traced over the curve twice, well then that would give us double the length. But we don't want double the length, we just want the length of the curve. So the theta values have to trace out the curve exactly one time. All right, so we actually looked at this polar curve before. We sketched this one, and let's just kind of review that a little bit just to see. But before we do that, let's get our integral set up except for the limits of integration. So we still need to figure out our limits of integration here. And let's just write down the formula. So the length is the square root of r squared plus the derivative of r squared. All right, let's fill in what we know. So the value for r here is 3 cosine theta. And then what's the derivative of this function? Well, derivative of cosine is negative sine. So the derivative here is going to be negative 3 sine theta, all squared. And we're going to integrate this with respect to theta. And I'm going to leave the limits of integration here kind of empty. We'll come back and fill these in a few seconds once we sketch out the graph. But let's just see how this is going to simplify. So, it's a fairly common mistake to make. We have a constant here times the trig function, and all of that's being squared. So when we square this, we're going to square the 3, and we're going to square that cosine. So we're going to square both of them. And that's because we have multiplication inside the parentheses here. So it kind of, the power here affects both terms. Same thing over here. We have a negative 3, we have a sine. When we square it, we're going to square that negative 3, and we're going to square the sine. So when we simplify this, we're going to have the integral of the square root of 9 cosine squared theta plus 9 sine squared theta d theta. And now that negative 3, when we square it, becomes positive 9. All right. So let's see how this thing simplifies down. And again, we're thinking we have trig functions here. I'm seeing some sine squareds, some cosine squareds. So we want to start thinking trig identity. And probably the one we use the most. Sine squared plus cosine squared is equal to 1. Now the only thing here is we have this extra 9, but it's on both terms, so we can factor out that 9. And really write this as the square root of 9 times sine squared plus cosine squared. And now we can simplify that. So, we started seeing some sine squareds and cosine squareds. Get that trig identity in mind and see if it's not exactly sine squared plus cosine squared, see if there's something you can do to get a sine squared plus cosine squared. So here, there were some 9s, but we could factor that 9 out and get the kind of the desired term here. And now sine squared plus cosine squared is just 1. So we have the square root of 9 times 1, so just the square root of 9. And this is going to be, once we find these limits of integration, this integral is not going to be too bad. So what's the integral of 9, or what's the square root of 9? It's 3. And what's the antiderivative of 3? Well, it's going to be 3 times theta. All right. So we're going to be able to do this once we figure out the limits of integration. This is the actual integration part of it is not too bad. All right, so how did this polar curve look? So let's think about we're going around the origin counterclockwise. And we normally start on the polar axis, so we start on the ray theta equals 0. And you just want to plug 0 into the polar curve here to see where you're kind of starting. So when we plug 0 in, we get 3 times cosine of 0, which is 1. So we get 3. So we're going to start 3 units away from the origin on the theta equals 0 ray. All right, what happens when theta is pi over 2? So we're just kind of working our way. We're going around counterclockwise, and we're just working our way. Start with the kind of the main rays here. So start with 0, pi over 2, pi, and see if you can kind of get a picture of what's going in. And then you can go to some of the other rays and maybe plot a few more points just to kind of get an idea, further idea. All right, so what about pi over 2? If we plug pi over 2 into this, cosine of pi over 2 is 0, so that means r is 0. So that means we're going to be at the origin. And if we were to, say, plug in cosine of pi over 3, which would be this ray right here, cosine of pi over 3 is 1/2, so we would get 3/2 when we plug it into our polar curve. And so that would be this point right here. And if we looked at pi over 6, we could figure out what cosine of pi over 6 is. That's square root 3 over 2. And if we wanted to get a decimal, 3 times square root 3 over 2, we'd get a point roughly out here. And that would be on the pi over 6 ray. And so going from 0 to pi over 2, doing counterclockwise, is we're going to trace out this curve, or this portion of the curve. And we've done this one before. And what we saw is that it's a circle. So going from 0 to pi over 2, we've just traced out half of the circle. And then going from, so this is what we get going from 0 to pi over 2. Now what about from pi over 2 to pi? What do we get going from those? Well, we get the other half of the circle. So you can kind of see, just start with a few, we have 2 pi over 3, we have 5 pi over 6, and then we have pi, and just plug these values into the polar curve. So let's start with 2 pi over 3. What do we get when we plug that into cosine? Well, we're going to get -1/2, so we get -3/2 here. So what does it mean when the radius is, or the r value is negative? Well, we're looking on our polar ray here, but when it's negative, we go into the opposite quadrant. So we're going to go down here and move away from the origin. Ends up being about 1 1/2 units away. So we're going to end up right around here. And then at 5 pi over 6, plug 5 pi over 6 in, we're going to end up with 3 times -√3 over 2, which would put us, again, it's going to be negative, so we're going to end up around here. And then at pi, what do we get when we plug pi into cosine? Well, we get -1, so we get an r value of -3. So if the r value is positive, normally we'd be drawing the point or sketching the point on the positive portion of the theta equals pi ray. But because the r value is negative, we go to the opposite side, and we'd actually draw back. We actually end up back at this point where we started. So we get the other half of the circle. So when we rotate, we go around the origin, starting at 0 to pi over 2. That gives us the top half of the circle. And then when we rotate from pi over 2 to pi, when we move in that and plot the curve for those theta values, that gives us this bottom half. All right, so we have some options here. So we know going from 0 to pi traces out the curve exactly one time. So we can use that and just fill that in here. So the interval is going to be theta between 0 and pi. So we're going to evaluate this. We're just filling it in here. All the while here we were doing a definite integral. So we did want to integrate this from 0 to pi. That's tracing out the curve exactly one time. So theta equals 0 is where we start. Theta equals pi takes us back right where we started. So it traces out the curve exactly one time. And we just need to evaluate. We've done all the integration. Now we just need to evaluate it between 0 and pi. And if we plug in, we end up with 3 pi. And this agrees with, what we know about circles. So this is, if we remember back, this was a circle of radius 3/2. So you can see the diameter here is 3. The half of that is 3/2. So this is a circle of radius 3. And what we're doing by calculating the length of this polar curve is essentially we're calculating the circumference of the circle. So what's the 2 pi times the radius? So what was the radius? It was 3/2. Plug it in. We get 2 pi times 3/2, and that's exactly what we found here. So the length of this particular polar curve agrees with what we know about the actual length. We know this is a circle. We know what we can calculate the length some other way. But this formula allows us to calculate the length of polar curve, more general polar curves, so things that aren't necessarily circles. All right. Now we did have another option here for the interval. So we could have used symmetry here. So instead of integrating from 0 to pi, what we could have done is we see that, once we know what the full sketch looks like, the full curve looks like, we could have integrated from 0 to pi over 2 and then just doubled our result. That's another option. So we could have also used symmetry here. So we could have used theta values between 0 and pi over 2. That would have given us just the top half of the circle, and then use symmetry. So integrating from 0 to pi over 2 would have given us the length of just that top half, and then just double your answer. Another option there. So sometimes that can be a little bit easier. If you want to simplify the limits of integration a little bit. Sometimes you can, find just a portion of it, what gives you just half of it, and then just double your answer to get the total length. All right, so this is really the idea here with the length of a polar curve. It comes down to just remembering that one formula. And what we're going to see next time is this kind of ends our discussion for polar coordinates and polar curves. What we're going to see next time, though, is kind of where this formula comes from in a more kind of generalized sense. So we're going to investigate this formula a little bit more and see how to find the arc length for not just polar curves, but more generalized curves. So we'll see that next time. All right. Bye-bye.